This talk I'm going to present is about the work I do at the boundary of computer vision and AI. And when I say at the boundary, I don't mean a very ambiguous concept of a boundary, a specific task, which that is augmented reality applications that benefit from the insights of both computer vision and artificial intelligence. And let me delve a little bit more in the details of this. Let's see. Let's start out by defining these very high sounding concepts as computer vision and AI. They're very simple in practice. Artificial intelligence is this set of technologies and methodologies that are developed for machines to perform tasks that simulate the human intelligence. That is, at the end, we're trying to help a machine behave as if it had the intelligence typically associated with humans. And to better convey this is to have a more exciting and difficult tasks that actually highlight this capability or similar capability to human intelligence. Computer vision is also a very in vogue field now, but at the end, if you want to define what we're really working on, it is very simple. We're trying to extract meaning and concepts from pixels. We're trying to go from whatever an image conveys into what it actually means and what are the underlying concepts that are depicted in an image. So these two things actually are very related. However, as currently there has been this very large gains in the interest in both of these areas, making intelligent machines and making machines that are perceptually capable. So turns out that this is a happy marriage here. Both of them can contribute, and the area of interest that I have focused on in the last couple of years is in augmented reality applications that take advantage of this ability to perceive the environment and the ability to reason about the environment. Putting those two capabilities or faculties together facilitates very exciting applications and systems that we developed. So let me first address the elephant in the room. You may have heard the term augmented reality, extended reality, virtual reality, mixed reality. There's a variety, a plethora of acronyms available, and the space may seem a little bit ambiguous and esoteric in some regards. Let me try to clarify what I talk about when I refer to augmented reality. So let's disentangle that alphabet soup. Consider that there's continuum of or a spectrum of your experience that goes from the reality to virtual or digital reality on the other end. On one end, you have your everyday life that's real. The other is the cybernetic environment. So consider that we have one of these options at the opposite ends of the spectrum. In reality, you see actual content in nature, and you see it without any display device. Perhaps, as I do now, you can wear a display device with your glasses to help you focus a little bit better. But the content you're seeing is just whatever resides or lives in your world. Augmented reality actually provides an enriched display through an external optical mechanism that augments or enriches the content that you can perceive. For example, if in real life you're walking on a trail, an example would be that now you are walking on a trail with some guidance that is overlaid with some type of display that you can actually wear, and now whatever information is contextualized within the environment that you are perceiving. So that is augmented. You provide additional information that in a very structured and environment relevant way. The next level of immersion, going from this reality to virtual reality experience, is to actually allow for interactive exchange of information between you and the virtual representation of some environment. That is, you can actually place virtual objects that are aware of the natural scenario, and you can see how their interaction between those virtual and real things actually modify the behavior of the system. So the if augmented is just about conveying national information, mixed or tends to be considered when there's this concept of interaction. And on the other end of the spectrum, we go to the virtual reality, where everything that you're experiencing is in this digital domain. It's not necessarily reflected on the natural environment, and that means that what you're seeing is typically in an actual closed display. That the only content that you see now is what is being rendered, and you don't see whatever is outside of your environment, and that's pretty good if you want to, let's say, take a break from the actual real environment. Okay, submit. So, so there is this spectrum from natural environment to virtual environment and in between. And typically, all these variations of augmented, mixed, or virtual reality, it's what we know as extended reality. So there are many variations that include the virtual world. And when you include the virtual world in your experience, that is extended reality. To the degree which you make that insertion, then it's either AR, MR, or VR. So hopefully this helps clarify a little bit when you see those terms out and about. Let's do a little bit of history here. The first system was developed way in 1968. That was the first system that incorporated this concept of a wearable display. There were computer graphics, but now we wanted to have a system that had this responsiveness to it and could be embedded with the user as it is moving about an environment. And in 1968, Sutherland and University of Utah, and previously MIT, had began work on developing this type of system. The idea is this was the first approximation to the head-worn display. And you can see on the left here some examples where you get a display that actually is binocular. You have two different displays, each one for each eye, and then you try to do the stereoscopic vision through the computer graphics. The device that you see on top is actually a mechanical head tracker. What's going on here is that through tracking of the movement of the joints, there's an estimation as to where the camera or where the observer has moved to. And the reason for the name is because in order to keep track of where the user was moving, there had to be always this strap to this device that was a hanging piece of metal to their head. So that is the source that was of the name. That was just intended for the head tracking system, not necessarily for the binocular visualization. At the time, graphics were not very developed, so they were showing some wireframes and some very simple depictions of the environment. Going forward, the next big step in actual augmented reality was scenarios for the Air Force training. Actually, the virtual fixture system back in 1992 actually had the same mechanisms, very similar mechanisms, where you had to keep track of the head, but now the actual servos or exoskeleton was available to the user, where he could actually interact, and there would be a virtual representation of these movements visible to the user in a reference frame equivalent to the real world. So basically, you would have some type of synthetic robotic arms that you could control that were actually corresponding to the actual pose of your natural arms while using this harness. And the idea was to perform simple task of trying to navigate a virtual environment. And this was a significant step up. So these are historical systems, but they were not very portable and they were very special purpose and research oriented. But let me talk about what the AR and VR systems typically compose of. Clearly, you need to have a mechanism to display this content to the user. In addition, you need to have a mechanism to keep track of how the camera or how the observer has moved in order to account to what will be the next content that will be shown to the user. So once you display something and keep track of how the user has moved, you actually generate what is the next content that you will need to show the user. At this point, you're just thinking about what are the general characteristics of this content. Once you know what the content you want to render or to present to the user, you actually have to then integrate it into something that is visible to the user, and that's what we call rendering. So once you have that particular output that you want to provide the user and to the display, you show it to the user, and this cycle repeats. Again, you keep tracking if there's any movement, and if there is movement, then you compose how the scene should look or what elements have changed in the virtual representation that you're showing to the user, and then figure out what the pixel values and how to render it to the user. Here we're considering an arbitrary display, but this may be another source of confusion. What type of displays do we work with when we're talking about AR and VR systems? Well, there are three main differences. Typically, the type of systems I work with are head-worn displays. That is, you put the pixels right in the field of view of the user in a natural way, in a way that is portable and adaptive to the location of the user. And to do that, you either show video as the work by Sutherland before, or as more recent, you provide some see-through display that actually allows you to see both the environment and whatever you want to display. Some more common and accessible systems for AR are those where the display is hand-worn. Basically, you actually carry the display, and that's when you have, for example, the AR on your phone, where you actually see the content on your phone of a virtual environment or an augmented environment. And some additional and very interesting work is when you have spatial displays. That is, you either have projectors that actually illuminate your environment with indicators of actions to do, or more the apparent geometry that you're being perceived, or more advanced are mechanisms for holograph, where you actually have displays that indeed provide visualization in 3D that can be observed by the user without the need of additional devices such as particular glasses or a handheld device. So we will see, as this technology advances, the proliferation of different types of AR systems and VR systems, and they will be working on different target displays. My focus has been mainly on the head-worn displays, as I will talk about a little bit later. But let's look at some examples of this type of implementations. One of the most, for me, prevalent examples of AR is one that I didn't even know was there. Hopefully you are familiar with this example. This is the first down line in the NFL football games. Turns out that since 1992, they've had an additional set of pre-processing for the broadcast of every football game, where the feed that goes directly from the uh, uh, broadcaster uh, is processed in order to on real time, uh, initially back in 92 with up to maybe a 3 second delay, uh, redraw or append to the actual broadcast feed this yellow line. And you can see here that yellow line had to be aware of what was the color of the ground, what was the color of the different players' shoes and uniforms, so that it wouldn't overlay over the action, such that it would appear as if it was painted on the ground. Yeah, this has been prevalent for many years, and now there's no longer the need for the extra 3 second delay to do the processing. Now it's very efficient, and the company that did this has changed to or expanded to different other domains. I think they also try to do the hockey highlighting stuff, and also for different sports analytics now. Um, More recently, my and I know this is what my kids associate with have associated with AR and VR systems. We have the Pokemon Go, location-based AR system where you would actually interact. You would use the phone as a window into this virtual world that was collocated with the real world, with the natural environment. So you would here's an example of you would actually have to find these individual characters, and they were located at specific areas, and they were um, physically attached to a location, and you had to visualize them through your phone. That was a very interesting uh, um, dynamic because it was very popular, and people actually went out of their house to look for them, and it was an uptick of people outdoor activity because they were actually on the street trying to look for where those Pokemon were to actually collect them. Another one of my kids, what the they think that I do when I told them that I work with augmented reality, he said, "Oh, that means that you can do one of these. Um, these are the avatars that are controlled by your own expressions. So as you move about, there is this corresponding deformation to this virtual character called an avatar. So as you move your head, the actual display makes these changes. This is was very popular a couple of years back when it came out as a feature for the newest iPhone. Something perhaps more prevalent that you may not even consider as AR uh, are the modern state-of-the-art head-up displays. Now they have incorporated augmentations that are not just the static content such as speed and fuel capacity and this stuff, but also provide uh, environmental aware or dependent content such as this is the street where you have to turn, and these are realistically presented environments. And this is as of 2021, they have very at least Volkswagen has a very effective uh, augmented reality through the head-up display. So this is another type of display that perhaps doesn't fall right in this uh, eye or handheld or head worn. But and recently, very recently, Apple actually introduced the promise of uh, novel dedicated devices just for augmented reality. Oh, sorry, I have a whole bunch of questions in the meeting chat that I had. Ah, uh, Okay, sorry. I just took a break to look at the chat to see if there was any pending disaster. Apparently not. Um, okay, and the idea of this augmented reality display device is that now you have a computer experience that is uh, based on these augmented reality concepts, and especially this concept of spatial computing, where the computer is or the device is aware of your spatial environment and accommodates to that geometry and properties. So the idea is that now things are laid out not in terms of a screen, but now in terms of a spatial distribution of overlays and widgets. And this is supposed to be available in the upcoming months. I'm happy to say that one of my recently graduated PhD students is actually working on this project. He got hired um, last July. He presented and went and got a position at Apple working specifically on this project. Excuse me a second. Forgot to mention, I got a little bit of a cough. Um, yeah, so this is very exciting because now it's going to provide this concept of augmented reality to a broader audience, as long as you can afford the $3,500 entry price for the device. Um, okay, so uh, this may, at first glance, may seem a little bit gimmicky in the sense that there's very specialized and very limited applications, but in reality, there's a wide spectrum of applications that are driving different companies such as Apple, previously uh, Facebook, now Meta, uh, and Microsoft to develop technology for this. Now, the current status of the market is such that there's a lot of uncertainty, but the promise is that all these technologies can have applicability to a wide gamut of potential applications, such as spanning from real estate. You can go to Zillow and see how your furniture would look there. What is the how would the house look from a particular location? There's fashion, a whole lot of virtual travel, and and even military applications. Actually, I will talk about how some of my research work is actually being funded to support these type of applications. But in particular, my focus is on solving not controlled environment uh, problems and very let's call it developer design scenarios, but rather doing the opposite. I want to build virtual assistants that can help the user solve actual physical tasks. On the left, maybe some of you remember the the virtual the clipping. I showed this to my kids. They had no idea what this was. They were, but they did know what the icon or the image on the right actually stood for. Siri. These were assistants included in the machine operating system to facilitate the use of the actual infrastructure that supported them. That is, the little Microsoft Clippy was designed to help you improve the way you use Microsoft Windows. And Siri is a mechanism to help you better streamline the access to the facilities that the iOS provides. But they are assistants. They are there to help you use the same machine. So there's kind of a advanced sorry, advanced helpers or help systems because they are just their domain is to use or to interface with the actual system where they reside. We want to build systems that actually help people use or solve practical problems in the real world. So to that end, I've been lucky enough to be part of a research collaboration, multi-institutional work that involves four different universities. This is the snapshot of our team. It is a collaboration on a DARPA project that involves the University of Michigan, the University of Rochester, and Purdue, along with students. And the project is about perceptual task guidance. The idea is we use these head-worn displays that actually not only serve as displays, but also as sensors that actually capture the environment. And based on that observation of the environment, we want to be able to interpret what's going on on a given task and give the user some feedback as to how the user is performing that particular task. So basically an assistant that helps you or teaches you to do something better. Excuse me. Sorry. Okay. So perceptual task guidance. It sounds like a very abstract concept. And we define it as this task of building an augmented reality apparatus that has physical reality. But all of that is very complex concept. Basically, what we want to do is we want to understand the task, understand the user, and the actions that he has undertaken, she has undertaken to carry out that task. Sorry. So doing this requires full automation, requires the system to be interactive and responsive to the actions of the user, and to customize to a specific task, but also have a generalizable enough architecture to the same architecture be applicable to different problems. So let's talk about the problem of perceptual task guidance. At the center is this specification of how to help the user do a given task better. It obviously requires knowledge from augmented reality. The interaction we want to have with the user must be natural. So we have this speaking communication with the user. So we need natural language processing. We need human-computer interaction, because at the end we have a device we have to interact with. We need to actually know what's going on in the environment. So we need computer vision. We need to understand what a given task is and how to build computational abstractions of it. So process modeling is also needed, as well as audio and voice analytics. So we want to communicate in real language, but we also want to listen to the user in real language. So very broad and quick view of the process can be seen here. Originally, this is the overall rationale. Let me go through the components here. We differ from existing technology in the sense that we don't want to actually hand design a system for each task, but rather our goal is to obtain information about the task, like a recipe or a user manual, then use that information as the basis to build our abstraction of how the actual task behaves. What are the components? What needs to happen first? What are the dependencies? What is the data that we need? And all that should be built in an automated way. Once we have that, we actually devise a set of instructions and hints that we can provide the user, given that we know how the task should be performed and what is entailed within it. Importantly, we need to on the fly maintain visual or perception-based estimate of what is going on in the scene, and that needs to happen in terms of what's being observed and what's being heard. So we need to on the fly keep track of all this information. And finally, we need to have a system that, given access to all this knowledge, goes ahead and makes the decisions as to what type of interactions to have with the user, which means we also must model how the user is feeling and what is the perspective of the task. Okay. So let me quickly go to an actual example of how this works in the real world. This is our augmented reality cube solver. So this may sound a little esoteric. Let's get in the thick of it. Our problem is very simple. We want to take a Rubik's cube that is scrambled and get as output a new or a solved Rubik's cube. How can we help the user do this particular task? I looked around the internet to see what was available, and I found that there was this digital Rubik's cube that would actually change colors as you manipulate it and have motors in it that would actually give you a hint as to what actions to do in sequence to actually solve it. I saw some robotic tools that actually just spun the Rubik's cube about in order to solve it in a very completely automated way, which didn't give much satisfaction to the user, but at least you could see that the robot could quickly solve it. And there was this website that I found that has this Rubik's cube solver. So that was interesting. You could go there and actually get help on how to solve. However, we wanted to solve it using these augmented reality devices, and that's what we put effort into. So I wanted to base the solution on this type of systems, on the actual web page that helped the user. So let's see how that worked. That website, you needed to go and actually paint a copy of how your cube looked like. What was the configuration of the color distribution? And it had a nice app where you could actually move the faces and put the colors that correspond to your real life cube. Once you did this click for each one of the 9 times 6 faces, 54 clicks, you did all your 54 clicks, and you actually had a virtual replica of how your cube looked in real life. Once you have that, then the computer, the website would run a program that actually did the planning. And in order to what was the sequence of solutions that you needed, or sequence of movements that you needed to perform to actually do solve the cube. And it would just print out the sequence of solutions for you to actually follow. It will give you kind of like a recipe. It will give you a set of instructions on how to get to the desired output. And that was it. If you made a mistake along the way, then you needed to re-enter all your colors and then try again. So we wanted to improve on this. But the overall framework was, there was a mechanism for the input of the configuration, which was this coloring of the cube. Then there was an automated process of planning it, how to solve it. And there was this output in terms of a move list. This is what the website did. What we wanted the AR system to do was actually to, instead of you having to color, to just have the cameras on the device scan the cube, plan a solution, and then guide the user in the process of solving the cube. So to do that, we developed our own software for accessing the hardware level of all the cameras, all the nice electronic bits needed to be addressed. And then we built a user interface based on that. We wanted this system to be closed loop, in the sense that we wanted to be checking that what we're doing is in the right state. We wanted to have communication with the user that was visual and audio. And also, we wanted to have this spatial guidance, not just a list of what to do, actual pointers that were informative. So let me show you a video of how this system worked in practice. This is what you're gonna see here is what is being displayed on the user see-through display. This is exactly what the user sees. And I appreciate if you can confirm that you can hear the audio.
I'm not hearing any audio, Enrique.
Okay, perfect.
Going to scan the cube now.
Okay, let me go through that.
My purpose is to help you solve Rubik's Cube. Grab a Rubik's Cube and settle in. Let me know when you are ready to begin. I'm ready. We're going to scan the cube now. Hold the cube so the side with the white center is up and the side with the red center is facing you. Tell me when you're ready. I'm ready now. Show me the side with the red center. Make sure the side with the white center is up. Show me the side with the blue center. Make sure the side with the white center is up. Why are we doing this? I'm scanning the cube with your help. I need to scan it to find the solution and help you solve it. What should I do next? Show me the side with the blue center. Make sure the side with the white center is up. Show me the side with the orange center. Make sure the side with, show me the side with the green center. Make sure the side with the white center is up. Show me the side with the white center. Make sure the side, show me the side with the yellow center. Make sure the side with the green center is up. Scan complete. Now, we'll tag this cube together. I'll be quiet while you handle the cube, but feel free to ask for help at any time. Tell me when you're ready. Go ahead. Turn to the left. I think so. Turn the bottom layer a quarter turn to the right. Well done. You solved the cube. Here, reset to start over.
Okay. What we saw here is a system that indeed could recognize what was being performed and was able to interact with the user in a two-way communication. That communication could be verbal and visual. I'm sorry about this. In addition, the text that you're seeing here was actually displayed to the user. These are not captions overlaid on the video. This is just the output that was given to them, and at the same time, output to the speakers on the device. So this is a system that actually incorporated all this state estimation and closed loop verification and bimodal communication with the user on real time on a specific task that's physical, or that it is in the real world, not something that we want you to perform arbitrarily designed by the developers, but rather some an actual real world task. So
hello, I'm Mark.
Okay. So going forward, we're excited because computer vision has a lot of applicability in AI also in determining how to track the user, how to generate content, and how to actually render that content to the display. I'm very excited about multiple aspects here, mainly about new capabilities for image-based rendering they're very flexible and very robust and very high accuracy, and reduce a lot of the necessities for building explicit models of the environment, but rather you just learn how to render content based on examples. And this is applications of machine learning and image rendering that are very exciting for the future of AR applications. Then we have all these generative models that facilitate the creation of content based on arbitrary prompts. You just give the system, give me an astronaut riding a horse, and this is what you get. You can get more creative. You can say, teddy bears working on AI research on the moon in the 1980s, and this is what you get. This is synthetic images that were generated from textual prompts. You want to see how Homer Simpson would look in the Psycho movie? Well, this is how it would look, according to the AI system that generates images based on actual requests from the user. More importantly, the recent advances in large language models allow to learn from large swaths of text and images and speech, and learn models that are general purpose, that you can adapt to diverse tasks such as sentiment analysis, question and answering. And those are the behaviors that we expect to incorporate more and more into our two-way interaction with the user. So going forward, there's a lot of opportunities for advancement in research and making our systems more general and more effective. So I think I'm a little bit running late, so I will stop here. And thank you for your attention.
So Enrique, this is Frank Bastano. Thank you very much. That was an excellent presentation. We didn't get any Q&As, so we'll see if there's any questions that want to come up now. But I do have one for you that I was intrigued by at the very beginning when you showed the sword of Damocles at the beginning of your presentation. What was the computer in the background that was actually driving all that?
Oh, you can. Oh, I actually don't know the specs, but this was the state of the art in graphics in the 1960s. Back in the day, you had to have a large rack just to do the equivalent of the current graphics card that you have in your laptop. You need to actually have this large parallel system or highly parallelizable system in order to perform all these operations on the pixels. I was lucky enough in my work at UNC Chapel Hill to actually be involved in the access or have access to this type of devices that were just going all out technologically at the time in order to draw some lines in the display of the user.
Thank you. In the last few minutes, are there any questions? I think Johnny, I thought you might wanted to try and ask a question. Did you have one for us?
Oh, no, thank you.
Okay. Any other questions before we wrap up our session? Okay, well, again, thank you very much to both Enrique and Dave for giving us an update on these fascinating topics. I really appreciate it, and hopefully we can have other interesting presentations like the one we had today. And as Sue said at the beginning, this has been recorded, and we will post the entire video and notify everybody that registered where they can actually see it and play it again. And for those that registered but weren't able to show up, they'll be able to view it at their leisure. Sue, anything else?
Just reiterate a big thank you to Dave and Enrique. This was a wonderful presentation. I learned quite a bit myself, so we appreciate that you're taking the time to give us this presentation. I will be sending out the recording of the session and a survey to all participants, hopefully on Friday. So if everyone could take a look for that, and hope everyone has a great evening.
Dave, did you have something to say? I think.
Well, I want to thank you for the invitation, but I also wanted to point out someone did post a question in the chat.
Was there
We
any
missed
check?
one? Oh, what device do you?
I'm really fascinated by your research, Professor. I have got a question for you. Image processing are very performance intensive. What device do you use for AI and AR?
Yes, this is indeed a challenge and a trade-off. Right now, we are using mostly the capabilities available within the head-worn device. In this case, the HoloLens by Microsoft, which actually is a computer, but the capabilities are fairly limited. Actually, most of our compute power is spent doing a lot of on-device compression in order to send the data to a workstation that has multiple state-of-the-art GPUs in order to do the image analysis on a remote scenario. But to do that, we needed to actually be able to get the information out of the device and transmit over the network in order to offload this correctly estimated excessive computational demands. Yeah.